Hi, my name is Dan Hall and I'm the Director of Field Operations at Objectivity. In this video I'm going to present the unique features of InfiniteGraph that allow it to do graphs at scale, and I will present InfiniteGraph's unique approach to weighted queries. Finally, I will demonstrate the power of our do query language on an InfiniteGraph database with over 10 billion graph entities in it. One of the core strengths of InfiniteGraph is its write throughput and ingest performance. Since InfiniteGraph is built from the ground up to be distributed, we're going to be able to use our patented pipeline technology to build clusters very quickly. While most graph databases will demonstrate their queries on small data sets of 10 or 100,000 data items, we can quickly build proof of concepts with tens of billions of nodes and edges. This graph was taken from a recent customer proof of concept, where we were able to meet the customer's requirements of over 1 million write operations per second simply by scaling the cluster size up as required. One of the things that separates InfiniteGraph from other graph databases is its ability to represent complex data. Unlike many of the popular graph databases that use a property model to represent the attributes on data items, InfiniteGraph is a schema-based database. This schema-based approach to modeling data allows a user to create much richer data models. This is a huge advantage when it comes to creating complex edge types. So for just a minute, it will help if we talk about edge modeling. The demo dataset models phone calls between phones that are owned by people, and each of these entities are represented in the database as nodes in the graph. A simplistic way to model something like calls is to take the phone entities and connect them together using call entities. So if phone A calls phone B several times, there will be a separate call edge between those two phone objects for each call. If there are hundreds or even thousands of calls between two phones, you will have that many separate call entities representing that many different paths between the two phones. Although this simple approach would probably work, it's highly inefficient and it would actually slow down navigation because there are so many paths to process. The real relationship here is actually between the two phones and the fact that they've called each other at all. InfiniteGraph allows us to improve our model. Once a call edge has been established between two phones, that relationship exists, and the details of each individual telephone call are really just extra details on that call relationship. We can accomplish this by creating a call detail entity for each of the telephone calls and hanging those off of the call node. The more phone calls that are made between two phones, the more call detail entities we add to the call object, and the more interesting the relationship becomes. Many graph databases can't support this kind of complex data modeling for edges. In addition to complex edge modeling, InfiniteGraph offers something called placement. This allows the user to specify where data items get placed in the database. In our case, we can specify that the call and call detail data items are related. InfiniteGraph uses this information to physically store the call detail data items close to the call data items that they're related to, often on the same physical disk page. This means when queries are being performed that traverse call edges and use the associated call detail data items, the call detail data items will be loaded from disk at the same time as the call data items. This optimization may sound like a very small detail, but when you're working with billions or trillions of data items, this results in an incredible improvement in query performance, and many graph databases, most in fact, do not offer anything like this at the physical layer. Another background topic that I wanted to cover is the concept of edge weights. When working with graph data, users are often interested in some aspect of the relationship between the individual entities. Consider a map where towns are the nodes and the edges are the roads between the towns. We could say that the edge weight is the length of each road. We could then use these edge weights or distances to find the shortest path between two towns, say A and H. by finding the path with the lowest summed edge weights. This is a very simple and straightforward example, but it's very important in the world of graph databases. But edge weights are not just about distance. In another example, we might have several people that are related in different ways, and express the relationship between them as a weight. Sam and Bob work together. Bob and Sue are friends, Sam and Lisa are siblings, and Lisa may have used a phone to call Sue. For some situations, it's reasonable to assign a fixed value to an edge. In this example, every works with relationship might get assigned a value of 5. Every friends relationship gets a value of 3. But what about situations that are more dynamic? Is it sufficiently descriptive to assign a fixed weight to every called relationship? Or would it be better to have the weight reflect the number of times one person called another person? If Lisa called Sue 1 time, how important is that connection? Probably not very important. But if Lisa called Sue 3 times a day, every day for 3 years, that makes the relationship between Lisa and Sue comparatively more important. In many cases, we want the edge weights to reflect these kinds of dynamics within our graph. InfiniteGraph, through its do query language, provides us a rich set of semantics to capture these kinds of dynamic relationships. This brings us to the weight calculator. The InfiniteGraph do query language allows us to define something called a weight calculator. A weight calculator specifies a mathematical formula for calculating the weight for our edge types. In this simple example, we are defining a weight calculator that computes the weight for a call edge. Associated with the call edge designation is our formula for computing the weight of a call edge. That formula says to return 1 over the maximum of all call detailed duration values associated with the current call, designated with the C variable. This is a very powerful capability. I can now compute the weight of an edge based on data that resides in the edge data item itself, as well as data items connected to but outside of the actual edge data item. This is a reasonable approximation of how 2 phones and their owners might know each other, because people who know each other tend to call each other for longer periods of time, and that lets us assign higher weights to people who engage in longer duration calls. And we can do more. The do query language allows us to qualify which call detail entities we wish to include in our search space by simply adding a predicate. Here, our edge weight is based on the count of all call detail entities that have a start time after a specified date and time and a caller area equal to a specified value. Weight calculators are an extremely powerful abstraction. We can define several weight calculators and use them among different queries to gain different results and insights into the data sets that we're looking at. I hope this brief introduction has given you some insights into some of the unique features of InfiniteGraph that allow it to do graphs at scale. Now it's time to switch over to the Studio tool and show some of the real queries on data sets of over 10 billion objects. This is the InfiniteGraph Studio tool, and it's our data management and query web interface. We are looking at the storage view and we see some basic database information. This cluster is actually hosted on AWS, and I'm using a browser to connect to the Studio server running on one of the machines in the cluster. You can use the storage view to actually drill down into the various partitions of the cluster to see how the data is stored and distributed across those partitions. We can switch to the typewise object count view to see a statistical overview of the objects in the database, and here we can verify that there are indeed 10 billion call detail objects in the database and over 10 billion total objects. This data set was synthetically generated based on a statistical formula that ensures the data has a realistic distribution of calls and call details over a population of a given size. We can switch to the Do tab in Studio to execute queries. The Query Manager serves as your query history and allows you to recall and rerun previous queries. Let's start by demonstrating some SQL-like queries. This query says we're going to select asterisk from person with a specific name. And when we run the query, we get back a single entry. It's worth pointing out that though InfiniteGraph is known for graph navigational query performance, it can also be used as a general purpose database. This is a simple select on a person by name. Notice that it returns tabular results showing the fields of the person type similar to a traditional database. In this case, there are only about 5 million people, so let's try something more difficult. Our next query says to select all from call detail where caller area is 10403 and the start time is between 2019-3/7/1600 and 2019-3/7/1615, a 15-minute interval. Since InfiniteGraph is a distributed database, we're able to execute this query in parallel across all of our partitions. In many cases, ObjectivityDB can outperform native SQL databases even in this tabular style of query. Now let's take a look at navigational queries. This query is going to find all paths from a specific person out to the phones owned by that person. As you can see, Studio automatically represents these results visually in a graph. If we run the same query but go out 3 degrees, shown here, we see that this query represents a substantially larger set of data. Consider that each of these neighbors will have a similar sized expansion in the next level of the graph. Deep navigational queries in this very dense graph are very simple to write, and InfiniteGraph takes care of managing the large volume of resources necessary to complete the query. Weighted queries allow us to target interesting connections in the graph by controlling the graph navigation based on the computed edge weights from the graph. Let's define the weight calculator from the earlier slides, which uses call duration as a measure of importance. Now that we've defined our weight calculator, we can run a weighted query using that weight calculator. This weighted query constrains results by limiting the total sum of the edge weights along the path. It's important to realize that non-qualifying paths are being pruned in real time and not just filtered out in some subsequent step. This allows us to find deep connections that are strong and in this case may identify a chain of people closely connected to each other. Notice that this example is allowing up to 100 degrees of separation to be searched. This represents potentially billions of candidate paths, but Objectivity is able to quickly identify the most interesting results. Many of these paths are extremely deep and it would be impossible to discover without the use of weighted queries. While an open weighted query like the previous example is useful for discovering unknown connections, we are also able to specify 2 people we wish to find a close chain of connections between. This example again searches very deep, cutting through billions of candidate paths to produce the most interesting connections by limiting the overall path weight. The do query language makes complex queries like this very simple, and InfiniteGraph does an excellent job managing the resources that are necessary to complete this query and render the results. I hope you've found this presentation useful and informative. Please visit our website www.objectivity.com for more videos as well as information on all of our products. Thank you.